So, hi everyone. Thank you very much for coming. It's real nice to see all of you here. And this will be talk about application design and our approach to make it easier and more enjoyable. So, first of all, let me introduce myself. So, Kai from Subtle Mind, an Irish software development consultancy. We focus on the productivity of engineers and team efficiency, and are big fans of Scala and pure functional programming. We contribute to a variety of open source Scala projects. If you use Scala, most likely you use our contributions directly or indirectly. If you use Zio, you definitely have our code in your class path. As a consultancy, we help our clients make their teams more productive. The primary blocker for productivity is complexity. There are various kinds of complexity, for example, computational complexity. But what makes projects extremely expensive and sometimes destroys businesses is maintenance complexity. We help our clients fight complexity in their software development pipeline, and we create various tools in order to do that. Engineers often try to avoid dealing with complexity by shifting it right, by pushing problems later, pushing problem detection into the future, and on the next participants of the software development pipeline, possibly even all the way up to users themselves. For example, engineers may use a dynamically typed language instead of a statically typed one. This may sometimes allow them to deliver a prototype faster, but it will inevitably cause more issues to be found later on. In production, and would complicate maintenance if the code base becomes bigger than several thousand lines of code. The shift-left approach means that you should try to rectify potential problems as early in the development lifecycle as possible. Most of the sophisticated approaches we use, such as statically typed languages with expressive type systems, automatic testing tools, automatic acceptance testing, and functional programming itself, are all designed to shift problems to the left. I would insist that shifting problems to the left always pays back, but it's not always easy to actually do that. So we have many useful and sophisticated tools, but we still suffer from complexity. Often we can prototype an idea in a week, but it can then take years to turn this prototype into a working product for the end user. What's wrong? Most of the tools we use aren't composable, and it's very hard to integrate them. Approaches which work for programming tend to often fail for engineering, and in many cases, engineers agree with programmers without even realizing that the argument itself doesn't make much sense. So engineering is more about integrating components into robust maintainable systems, while programming is about implementing separate components themselves. So most of our efforts at fighting complexity have condensed into our own little framework called Izumi. It consists of four components: bio, Logstage, IdeaLingua, Distage. Bio is a set of CATS effect-like type classes for bifunctor effect types. Logstage is a structural logging framework, which can extract structure directly from string interpolations. IdeaLingua is an ergonomic interface definition language and an RPC framework, sort of like protobuf or gRPC, but it's also subject for another talk because it's too big. And Distage is the most advanced and most powerful dependency injection framework in Scala or any other language. And in fact, it's a lot more than just a dependency injection framework. I have to stress again that Izumi itself is loosely coupled. All of its components may be used independently of each other. For example, you don't have to use bio if you use Distage, and vice versa. So bio is a robust set of type classes, which you may use to make your code cleaner, separate concerns, and get all the other benefits of tagless final style. Also, bio cleans up your code by providing a summoner called F, which provides uniform access to type class methods. Only those methods of the type class that are currently visible and are in implicit scope are going to be visible in your IntelliSense hints. Also, you don't have to write any wildcard imports. Just let the IDE auto-import your type class names, and you'll get all the syntax extensions like map and flat map for free, without having to remember a magic retail like CATS, import CATS syntax, all and that stuff. So Logstage makes it easy to have structural logging. Just write your regular string interpolations, and you'll be able to turn text logs into JSON by flipping a configuration flag. Just Logstage alone allowed the telecom giant in the US to deliver a huge text traffic routing system a lot quicker than they originally planned to because log analytics were very important for them and they got their logs structured for free. So before we proceed to talk about the most important component of Izumi, namely Distage, let's discuss the abstract concept of a module. A module is a self-sufficient and reusable collection of types and functions which represent a solution for a domain-specific problem. A module can be described by its interface, and late module binding is a powerful way of fighting complexity. Many functional languages do not provide object-oriented capabilities, and many functional programmers argue that OOP is bad. While true OOP doesn't work well for modeling data, but a limited subset of OOP works excellently as a way to encode modules. Scala is an exceptional language which provides a rich set of functional abstractions, so you can module your data and processes with ease, and it also provides you the best-in-class encoding for modules. This encoding is disguised as OOP, and while Scala's modularization capabilities aren't perfect, there is currently no other language comparable with Scala. I will specifically highlight type members and incoherent type classes as unique and powerful Scala features. So it's good to have an encoding for modules, but it's not enough for composability. Modules depend on each other, and we need to compose modules into working applications. The common term for doing that is called wiring. Wiring isn't easy. First of all, it's not well defined in formal terms. There are many aspects that could make it hard, such as ordering, compatibility, configurability, error handling, lifetimes and life cycles, and more. It's extremely counterproductive to solve all these problems manually, and we need comprehensive tools called module resolvers in order to handle the wiring problem. So, for its solvers, the industry ran into the wiring problem first and created reflection-based dependency injection frameworks in Java and eventually in every other language to tackle the problem. In academia, the wiring problem or dependency injection frameworks are rarely acknowledged. The problem usually remains hidden and without a formal definition. However, some programming languages such as Scala tackle a related problem, type-based resolution of type classes and implicit values. Most languages other than Scala, and this includes Rust, Haskell, and OCaml, impose a coherence requirement for on this type-based resolution, requiring a single implementation to be defined globally for type class instance. This makes this mechanism extremely mismatched for managing application components. For application components, it's natural to have multiple implementations, such as for testing. Application components can depend on local variables, and this prevents them from being defined globally. And of course, globality means that no useful lifecycle can be defined for an application component if it is defined as a type class. While Scala does not require coherence, all Scala's implicits can help you with is pass parameters values into parameter slots of a matching type. They don't help you swap component implementations. They don't help you wire effectful components. They don't help you manage life cycles. So there is, of course, a third solution, the no solution, wire everything manually. This approach requires discipline and usually fails to scale. Refactoring becomes hard. Changing a module's dependencies, splitting, or joining modules requires changes at the wiring points. More modules, more changes. Often modules are assembled into hierarchies to try to contain complexity, but this in turn creates unnecessary coupling between them. Sometimes programmers give up and unnecessarily split an otherwise good system into microservices, just to assert boundaries between modules. When that happens, nothing good has been achieved. Instead of using a DI framework within the application to manage complexity, the same job is now being done by an orchestration framework such as Kubernetes, which is now used just to assemble the components of the system together. So we present our solution. Distage is a library which formally defines and solves all aspects of the wiring problem in Scala. So Distage is dependency injection, also known as wiring. Distage makes it easy to write multi-modal, configurable applications which can switch between different components in a sound manner. Distage allows you to stop choosing between monoliths and microservices. You can write monoliths which have all the good properties of microservices, or write microservices which can be run together as a monolith. So Distage makes setting up test dependencies effortless, and it can soundly share dependencies between tests. Distage can manage external dependencies of your application, such as Docker containers, and we call this scene management. Distage does all this without Java reflection, so it works perfectly with GraalVM native image, Scala.js, and Scala 3. Also, Distage has strict compile time checks, so that wiring problems are shifted left, and you don't have to run the application to find out that something has been missing at runtime. So I guess everyone knows what dependency injection looks like. You just somehow throw recipes together, tell your DE framework what you need, and magically get an instance. So Distage can do more. In this example, there is a repository interface with dummy implementation and a production implementation. Also, we have a service that uses the repository interface and application endpoint that uses the service in turn. As a side note, a dummy is a handcrafted test implementation of an integration point. Dummies are similar to automatic mocks, but they are not auto-generated. Sometimes they're also called fakes or manual mocks. All the components and their implementations are defined declaratively using the module def DSL here. Also, you can notice there are two possible implementations of repository, one marked repo dummy and one marked repo prod. When we want to run our app, we have to provide activation options to it. And activation is a flag that tells our application which implementation should you select for this particular run. If we provide activations through the command line, as done here, our application becomes multi-modal. It can run using multiple modes. As a side note, I should mention that Distage can wire code written in tagless final style and has native support for ZIO and cuts effect. But you might also wire plain code that doesn't use IMonads or tagless final. Now let's talk about multi-tenant applications. Essentially, a multi-tenant application is an application which can run several so-called roles. Here's a code snippet showing a role definition. A role is just a replacement for a main method. But unlike main methods, there may be several roles in one process running at the same time. Every role can have its own command line options, and usually every role runs in a separate fiber for itself. You may think of a role as a microservice, but it has the ability to run in one process with other microservices. Roles allow us to easily run multiple components or multiple microservices in a single process for either for simulation or to simplify deployment. And we use the term multi-tenant applications for applications that can run multiple roles. So on the bottom half of this slide, there are two examples of running a multi-tenant application from the command line. So the first line has two roles called users and accounts, and it runs them with production implementations for repos and for transport. And the second line runs these roles with dummy repositories and a virtual transport layer. That may be very useful for quick simulations, which are crucial for thorough testing. Roles are extremely important because combined with dummies and multi-modal DI, they allow us to instantly run perfect simulations of our whole product with a single command line. This, for example, allows front-end engineers to instantly launch and reset their individual simulations of the back end. So there is an approach to testing which is hard to implement without a good DI mechanism called dual test tactic, which is very available to in our arsenal. The idea behind it is simple. We run the same test twice, with real implementations of our integration points and with dummy implementations. And we skip real tests if test dependencies, such as local SQL database or Docker daemon, are not present. It sounds simple, but it's in fact an awesome approach. First of all, it allows us to prototype business logic quickly, without being distracted by aspects specific to our integration points. So this in turn enforces solid design. We have to create better abstractions to accommodate both the dummy implementation and the real implementation. And this makes our code more readable and easier to maintain, simplifies onboarding of new team members. Some say that testing with just dummies is not enough, and because it does not reveal problems specific to real integrations. That's true, and which is why we promote dual tests. Moreover, some say that benefits of writing dummies aren't worth the effort, or that it's very hard to write good dummies. Well, in our experience, the return from good dummies is an order of magnitude higher than the time we spent writing them. As a side note, I would like to say that we prefer to use, say, dummy instead of mock, because people often think that mocks stand for automatically generated mocks. Automatic mocks break encapsulation and are generally evil, so we don't use them. We write manual mocks or dummies instead. So Distage allows you to set up dual testing effortlessly. So in this example, we have an abstract test suite. Each test case is a lambda, that returns an effect. And in its parameters, each parameter defines a dependency. And here we define several environment traits. Each environment trait defines a test suite configuration. In this example, we define dummy-env for tests for repo dummy repositories, and prod-env for tests with repo prod repositories. Then create our final test classes that extend our abstract envs. And that's it. Our tests are wired automatically, and they're also multi-model. So if we run the service prod test class, our tests will run with repo prod implementations. If we run the service dummy test class, then our tests will run with dummy implementations. And if we run all tests of the project, for example, using SBT test command, we'll test our business logic twice. The first time we'll test against dummy implementations, and the next time we'll test against real implementations. So this is a dual test tactic implemented with Distage Testkit. So most applications require their surrounding environment to be preconfigured in a certain way. They may require external services or local daemons to be available, or they may require the file system to be arranged in a specific manner. We call this required environment a scene. So in this metaphor, our application is like an actor in a theater. They require the scene that they can enter to be set up in a certain way before they can appear. Now, an application can actively create a scene on its own. It may spin up Docker containers with databases and use them instead of connecting to a remote database. We call this a managed scene. If an application expects someone else to provide the scene before it's launched, we call this a provided scene. Remember that as part of dual test tactic, we test not only with dummies, we must also test against real implementations. And to do that, we have to set up those implementations. For example, we may need to set up a Postgres database to use the tests. Setting up those external services manually using tools such as Docker Compose is not a nice experience, so you shouldn't do that. The Distage Docker extension lets you add Docker containers to your wiring and manage them in as normal components. Specifically, you can use them in your production tests to make both development, onboarding, and maintenance experience much better. You can also use managed scenes not only tests, but when running the application itself. This lets you run compact simulations of your product locally, which may be more accurate than running with dummies. Components with a life cycle, also known as resources, can be wired into the object graph using the from resource operator. Resources will be effectively acquired and released according to their dependency order and will always be finalized gracefully, even in case of an exception. In addition to the in-house resource type code lifecycle, you can also natively wire library types, such as the resource type from Catzelfact and various resource types from Zio, like the zmanage, zlayer, and the scope Zio. A common problem with tests and real implementations is that dealing with the sharing of very heavy components. So a heavy component such as a Docker container may take a lot of time to launch and require a lot of resources. You may not want to recreate it for every test, but instead create it once and reuse it in all of the tests. Usually people solve this problem with hacks, global variables, shutdown hooks, etc. Often these hacks cause problems later on. Distage has a principal solution for this problem called memoization. In this example, we declare a DB driver to be shared across all of our tests in all the test suites of the artifact that inherit from the DB driver env, not just this single test suite. As you can see, it's very simple. There are no global variables or shutdown hooks involved. Unlike with global variables, we're not limited to memoizing one DB driver globally. If we have different configurations in our test that require us to test with multiple versions of DB driver, we can do that too. Also, DB driver will be finalized immediately after all the tests finish. Another feature of Distage is integration checks. Integration checks allows us to define a simple precondition check which would prevent our tests or the application from starting up if the check returns false. So this code example on the screen defines an integration check, and as you can see, it's fairly easy to do. Integration checks run before all the startup actions, providing you a very fast feedback and allowing your application to fail as early as possible if an external dependency is missing or broken. In case of tests, this allows you to skip those tests and run those tests that you can run. They also help you implement the dual test tactic. Skipping the test that can't run without external dependencies really simplifies onboarding. So someone that starts with a project doesn't have to set up all the parts of the environment before they can start hacking. They can just clone the repo and run the tests immediately. So recently, we've released a new major version of Izumi, Izumi 1.2. So we've updated all the libraries in the framework to support Gas Effect 3, ZO2, and ZO2's new features, such as Scope Zio. We've ported the library to Scala 3 and made a huge amount of improvements. We also added a new concept called subcontexts that I'm going to talk about right now. So there often arises a problem when you have an infectious piece of data that you may need to thread through the entire application, or a big part of it. For example, suppose you're doing distributed tracing and you want to carry around a request ID to use it when logging, recording metrics, or adding it to exceptions, etc. You only get this request ID when your service receives the request. It's local, ephemeral data. It's not available at the beginning when you're doing the initial wiring of your components. One way to address this is to just add this local piece of data or an environment as a parameter to every single method everywhere it's required. Well, that's pretty ugly, and we don't want to do that. Another classic FP solution is to use a reader mono transformer, also known as a Kleisli. When we flat map on the Kleisli, the environment will be implicitly passed around for us, and we'll be able to access it when needed. Unfortunately, instead of infecting every method's parameter section, now Kleisli infects every method's return type. Moreover, mono transformers are extremely cumbersome to use, even in languages where they are an integral part of the language, and Scala is not one of those languages. So we're opening ourselves to a world of hurt by spreading the Kleisli everywhere. So what can we do? We may notice that we can always transform a class which requires the same parameter in every method into a class that requires the same parameter in its class constructor. Effectively, we can always partially apply every method in the class and end up with another class with one fewer parameter on its methods. Well, I bet it wouldn't take you much time to figure out how to write a function to transform the first class on the slide into the second class. Unfortunately, this transformation isn't always that easy. Now that we moved our local environment into the class parameters, it shares space with parameters that are not local and that we're wiring using our DI. We have a whole bunch of components that all depend on local environment and on each other and on other components that are more global, that do not depend on environment, such as metrics and database. But we can't use our DI to wire all these components because they require a request ID, and we don't have a request ID because we haven't received a request. But to receive a request, we need to wire all of our components in the first place, so we end up stuck. So in Distage 1.2, we had a way to resolve this problem called subcontexts. Using make subcontext function of the module dev DSL, we can define a subgraph of components that depend on local data. We use local dependencies to specify that the local data we need to supply is request ID. Then at the usage side, instead of requesting a PetShop API, we're going to request a subcontext that produces a PetShop API. And we provide a request ID to the subcontext and receive a fully instantiated PetShop API component that we can use. Now, if you used Kleisli before, you'll notice that the usage side is very similar. We provide missing data and we call the method. With Kleisli, we do it the other way around, but that's frankly material. Although the usage side is similar, we achieved a beneficial transformation. We cleaned up our code and got rid of a nasty mono transformer. While Kleisli infects every method and forces our code to evolve around it, the fact that this subgraph requires a local environment is only visible in its implementation and in its wiring. The interfaces are now squeaky clean. And we managed to do all that without infecting every method with an additional parameter or without misusing implicit parameters. We simply exploited the fact that Kleisli is the same thing as partial application and partially applied our class constructors. As a side note, using subcontext does not compromise compile time checks, despite the fact that we deliberately define an incomplete graph where one of the components is missing. This is still taken into account, and if you make any mistake when wiring a subcontext module, there will be a compile time error. Now, what if we don't have a large graph of interconnected components that all require some local data? What if we just want to refactor one component that repeats the same parameter in its methods and float up that parameter to the class constructor itself? Well, for this smaller problem, we can make Distage generate a partially applied constructor using the make factory function. This is a small-scale solution for a small-scale local data problem, so there's a lot less machinery required to use it. So to summarize, complexity can destroy projects, but shifting problems left can mitigate it. We created the mini framework Izumi to help shift problems left as much as possible. The most important component of Distage, of Izumi Distage, solves the wiring problem in Scala. It provides an alternative designed to either monoliths or microservices by facilitating creation of multi-tenant applications with multiple roles. I also say with no reservation that Distage Testkit is the best testing framework out there in Scala or any other language, with cross-test resource sharing, dependency injection into tests, native support for effect types, native support for dual testing with dummies, and native support for Docker containers. There is no more better or more practical way to write tons of tests with maximum productivity, especially integration tests. And finally, we showed a cute new feature called subcontext that lets you use more DI in the small and reduce your usage of the reader monet by just passing parameters to constructors even harder. So that's it. Thank you for listening. There are several links on the screen. So the first link is for Izumi project itself, where you can find documentation, best practices, and the glossary of all the specific terms. The second link is the GitHub repository for Izumi project. And the fourth link is an example of an example project that uses Distage and Bio. It uses everything, and it's a great demo project that you can play with, run, and it shows a lot of features of it with the framework. And the fourth link is a blog that we post sometimes. So please subscribe to our Twitters, give us GitHub stars. And we're always looking for new challenges, so you can write us at team.mind.io if you want to achieve hyper productivity.